Hey everybody, Dave Lindbergh in Hong Kong with another episode of the THD Podcast. Today we got some guys joining us from the Minnesota area, a company called Warkwyn, independent audio design consultancy. So we're going to find out some information about Klippel, using Klippel to design your speakers. And so we'll get into that. But without delay, let's not forget about the Alti Association, and they got their conference suite coming up at CES in January. So I encourage everybody to check that out, see if it's the right outlet for you to get involved with CES. There's going to be a nice little buffet of audio companies there. So we encourage everybody to check that out and contact Barry. So without delay, Simon's up again in Japan. Good morning, Simon.
Morning, Dave. Hey, guys.
All right. And good afternoon, Ken Peterson and Jason Cochrane joining us from Warkwyn. How are you guys doing?
Gentlemen?
Yeah, thanks for coming on. So maybe just give a quick overview on yourselves, and then let's jump into what we're going to talk about today.
Right. Well, I'm the chief bottle washer here at Warkwyn, constantly spreading sawdust on accidents, and I also take care of what management needs being done, invoicing and sales. And my background is in architectural and environmental acoustics. Spent close to a decade with Electrovoice doing a product manager and also doing ease modeling. So I've been driving ease since mid to late 90s, when they came on little plastic wafers that we used to call floppy disks. And I still do a lot of ease modeling here at Warkwyn. One of the things we do independently is produce ease data for people. So, and I lean heavily on Jason Cochrane there. He's our chief Klippel engineer. So he really is a great speaker designer. I'll let him speak for himself.
All right. Yeah. I started off, designing speakers and measurements and transducers and crossovers and systems, for Definitive Technology, some other companies. And then we started using Klippel. And then eventually we started being the reps in North America for them. And Dan Degree of Misco Speakers bought the company, and I came to Minneapolis with it in 2015. And I'd spend most of my time working with Klippel, doing tech support kind of stuff, helping all kinds of different companies. But I also do design work at work and other test and measurement for in-house stuff and whatever seems to come up, that kind of stuff.
Okay. All right. Maybe we can jump into a presentation and kind of walk people visually through what we're going to talk about today.
Yeah, so one of the areas of interest is the new Klippel multi-scanning workbench. A lot of people in the industry are familiar with the Klippel laser scanning vibrometer.
Mm-hmm.
So I thought it'd be really interesting to go into a little bit of a presentation about that. We won't take up too much time, and we'll step through it pretty quickly, but it really gives a good idea of how that system in particular can really define a transducer from soup to nuts for you. So I thought we'd discuss that laser scanning vibrometer with the additions now of a microphone boom-ar you can see here and a new baffle. So we were discussing what Warkwyn does. Sometimes we have to do it all. Sometimes we'll get speakers from people who don't even know how to define their speakers. As you can see, this is a automotive speaker here, and we get a fair share of those. So it surprises us sometimes. We get large firms send us speakers, and they really haven't even done the smallest amount on them, even wondering what the TL small parameters are. So there's a good bevy of questions that we need to answer for them and to understand ourselves. So like I mentioned, the Klippel scanning vibrometer, now called the Klippel scanning workbench, can move through all of the different domains of the transducer. Electrical, we can measure then in the magnetic domain. We've got a B field probe that we're going to show you. And then we can look at the mechanical, which is really where the laser scanning vibrometer started. We can look at the vibration of the transducers, et cetera. And finally, now with the addition of the room separation module on the laser scanning vibrometer, we can look at the acoustic properties of the speaker and how it radiates, pressure level, and directivity and frequency response at virtually any distance. And with all these things, then we can take that data and put them into simulations, whether that be ComSol or whatever you happen to be using. So feel free to jump right in with questions.
So for the layperson watching, basically, you've got a driver design and you're going to measure it and then dump it into a simulation, and that simulation might be how that driver behaves in a particular cavity in a car door or in a box in a PA application, or all these kind of things is where you're driving from those measurement data. Is that kind of the nut?
That's right.
Okay.
Sometimes it does go to simulation. Sometimes it doesn't. Sometimes our work is done once we define what the speaker is. And we will relay that information via test data, and we may never hear from them again. But during the course of that, we may identify problems that they haven't been able to identify themselves, and I guess that's what they pay us for. So if we step right into these, we can start in the electrical domain, and most speaker people out there are familiar with teal small parameters and how we measure those and how we measure impedance. And essentially, we just hook up to the positive and negative spades of the speaker. We use four-wire Kelvin leads. And four-wire is important because stimulus is delivered on one pair of wires, and then the other carries the current. So we can negate any lengthy speaker wire. So we don't measure that as part of the system. We're simply measuring the electrical response of the transducer itself. This, of course, brings us right into one of the most simple measurements we perform, and that's the impedance measurement, one of the first places we start. Pretty standard impedance measurement. We can see that we've got a mechanical resistance at 140 hertz. And then, of course, we've got a DC resistance of the coil at 7.2 ohms. That gives us an 8 ohm speaker. One of the interesting things you can see about this speaker itself is that we've got a little bit of a, I don't know if you can see my mouse, but we've got a couple little bumps there between 1 and 2K. So when we see that, of course, our question is, what's causing that? But ultimately, at this point, we've just defined the electrical impedance of the speaker. 8 ohms, 140 hertz. I don't know if this is going to be a good subwoofer speaker, but seems like it might be good for an open baffle. And of course, let's face it, we're looking at a car speaker here, so it might work very well in a car door. Mm-hmm. So when we do this, we measure with a triangulation laser, and that is positioned. We usually point it right at the dust cap. Could be said that you maybe get a little bit more accurate by putting it on the edge of the dust cap, right on the voice coil itself. But this helps us measure excursion. It's really accurate. It's really fast, and it defines our teal small parameters in a matter of just 4 or 5 minutes. And when we do that measurement, we wind up with 3 different spectral signals. We've got voltage there on the left, and then current, and then we've got our laser displacement on the right. And then, of course, we can feed all this right into our teal small linear parameter model. It's an interesting chirp. So this is, you can see that we apply a little bit of white. Sometimes we use whiteout. Sometimes we'll use a little bit of masking tape. Sometimes the laser doesn't reflect very well off the black, so we'll add a little bit of white there. And we'll apply this multi-tone signal. If you're able to hear that. So once we place that, once we perform that laser measurement, we wind up with our teal small measurements. We've got our DC resistant, mechanical resonance, our moving mass, MMS.
When you're using the impedance and then this laser displacement, is this imply that you don't need to do an added mass or a fixed volume?
That's exactly right.
Find these parameters.
That's exactly right. I mean, if you don't use a laser for this measurement, then you need to use the delta mass method. And this is a lot cleaner, a lot quicker. Lasers aren't expensive, but when you look at the price of a laser over time saved over years, you'll find doing it with a laser just takes 4 or 5 minutes, and you don't have to futz with really anything. And of course, we wind up with all our teal small parameters. You can see we don't have our X max there yet. One of the things we need to do as well is we need to measure SD. But we can put all these into models, and of course, this is the basic recipe for a transducer. Of course, it doesn't tell us anything about how the transducer operates in the real world. We don't operate transducers, if at all, in a small signal, small domain. Anytime anybody puts on a speaker, they're going to push it. So one of the hallmarks of Dr. Wolfgang Klippel 25 years ago, I believe it's an anniversary, is coming up with measurement in the non-linear parameter mode. And for the teal small parameters, all of these are separate little computer modules that you put into the analyzer or more or less put into your computer. And then you pull them up as needed. So if we step back, this is a LPM module. So the lumped parameter module, otherwise known as teal small. So that's a Klippel computer module. If we want to look at things in the large speaker domain, we pull up the LSI, or large signal measurement. So what we do in large signal is we start to push the transducer a little bit more, and you'll see that you've got a voltage here, an ever increasing voltage here over time. This is another way we quantify the transducer past teal small parameters. And what happens here is once we start the measurement, it will do a quick amplifier check, and you can see below that is time in seconds. So an amplifier check takes 30 seconds. And then we move into our linear parameters, and this will again define our lumped or teal small parameters. And after 150 milliseconds, or I'm sorry, 150 seconds, we enter what's called the enlargement mode, where we start ever increasing the voltage on the speaker. And there are, as we do this, there are some safety stops that we monitor while the voltage is going up. We monitor heat. We monitor BL for excursion. We also listen very closely. We want to start putting in those safety mechanisms or backing down the voltage the moment we start smacking the pull plate or hearing the speaker chatter. I don't know if you can comment any more on that, Jason. Jason runs LPM LSI on the daily.
Well, you set it up to limit on a change in the suspension stiffness or a loss in the BL force factor as this voice coil moves away from the gap. Most speakers self-protect themselves, like you can't destroy them because the suspension stops them, but some prototypes are not like that, and you have to pay attention how far you want it to move. And once it gets to a certain excursion level, it holds it there. That's the flat part of the graph, while it defines all the rest of the nonlinear curves, which I assume you're about to see.
Right. Yep. That gives us once it settles down and it drives those parameters, we wind up with our force factor BL and our stiffness of suspension or KMS. The gray lines you see in those, right? So the red line is actual measured, and you'll notice down below in the graph, you've got a coil in, coil out. So when we do this measurement, it's important to make sure polarity is correct. And the gray lines on there are just there to mirror. And so you get an idea of asymmetry. And the same can be said for stiffness. So as you can see the coil going out in the force factor, that of course is the voice coil leaving the gap. It doesn't leave the gap. Sometimes it'll leave the gap and try to make it back in and clip on the edge. That would be a chatter that we don't want to hear. And then as the coil goes back, as we examine this, this might be an indication of voice coil asymmetry in the gap. So it looks like the voice coil is a little bit further out, maybe a millimeter out in this transducer. And then we can look at our stiffness, which is pretty symmetrical. So as that transducer moves out, it causes stresses on the surround. Sometimes that can cause distortion. But it's a good examination of where the voice coil sits in the gap and the
something I'd like to say about distortion though. Any of these graphs that do not have a flat line, they make distortion.
Right.
That's the idea of this.
Yeah. Good point. One of the other things that this helps us examine is X-Max, one of the big factors people want to know about and want to know about their transducer, especially car audio companies. You can imagine that in the subwoofer wars as well. One of the rules of thumb we use here is we will look at 82% here of the voice coil excursion in its rest position. That gives us about 10% distortion. But as we can see, if we look at 10% distortion or 82% of its X-Max, that's limiting everything pretty greatly just by having an asymmetrical rest position of the voice coil.
When we're talking about distortion here, it is not necessarily something that you would measure as total harmonic distortion. It may be other forms of distortion, or is it?
Right, mechanical distortions.
Well, each nonlinearity produces different distortions in different frequency bands at different levels. So all of them not being flat will make THD, but THD by itself is usually not a good indicator. What's worse is the intermodulation of the different nonlinearities, and that makes a lot more audible artifacts in the sound. And they mix together,
right?
And it's
that kind of gets down to the crux of it in a sense, isn't it? Because if you come along and you measure a frequency response and say that looks nice and flat, that should sound fine, but it doesn't. One speaker sounds better than another, and this kind of thing is peeling back the layers to find out where that comes from. Is that fair to say?
Especially as you turn it up. Like if you play the speaker super quiet where it hardly moved sideways, then it's not going to make much distortion because there's not much change in anything. But as soon as it starts moving and all of those parameters change, it makes distortion.
Right. And it's just like peeling an onion. You start digging deeper and deeper and you find more areas where distortion can take root. So that brings us into, so now we've defined our teal small, our lumped parameters, and then we've defined what might cause distortion in a large signal or more true to life application. When we do that, like I mentioned, we use a triangulation laser and it's just one single shot. However, now we move into laser scanning, which is really the base for which the turntable and the workbench was built off of. And this can really have some revealing results. So as opposed to a single location to derive our lumped and LSI parameters, we use an array of laser analysis. So what happens is you can see we spray the cone a little bit there so that we can get good reflectivity on the whole cone. And then depending on the level of examination, we could take up to 1,000, 2,000 points across the comb, or we could just simply do a cross section of it. When we get paid for this stuff, we want to analyze it as deeply as possible. So we will actually do a full examination, not just a cross section of the cone. And one of the benefits of doing this is that we can also derive a 3D geometrical model of the loudspeaker cone. So you can take that and you can put that into your CAD models, whatnot. And actually measurement looks a little bit something like this. This is sped up, of course. But you can barely see the laser dot there. And it just uses an algorithm to move to the quickest point to make the measurement, and that each point then a sweep is heard. There's no microphone measurement, so you can do this in your office if you can handle the noise, but no noise will impact this measurement. So it's you don't have to worry about having it in an anechoic chamber or anything. So that gives us our results here, and I'm just going to go to a different screen here and bring up the scan of actually what we have here. So once we do a laser scan, you can see that we have an actual representation of the transducer, and this is actually that transducer. We can animate that. We can look at a radiation analysis to see at what angle maybe gives us a different directivity. And then of course we can look at it in cross section. So down here, you'll see the total acceleration level. Right now, what we're looking at is total vibration. You can see it over here. Here you can see in the low frequencies, as it should, the transducer is acting pistonically. So if we start our animation, there you go. Everything is good in that transducer's world. As we move up, and you can see it goes down, it turns red, comes up, turns blue. That's an indication of phase as we move forward. We're still in a nice pistonic mode here. But what happens here between at about 800, 700 hertz is we start to get what they call cone breakup. And we start having some problems with the transducer. You can see I've got amplitude enhancement really high. I can turn that down a little bit and some smoothing. So we start to see some components that are in phase and out of phase, and some of them happening at the same time. As this red line displays complete total vibration, this dotted line displays pressure level. So in a perfect world, your pressure level would be the same output as the red line. But as we start having some destructive components and breakup, our pressure level there drops. And it's interesting, when we saw a problem in our impedance between 1 and 2K, we're starting to understand what's going on there. You can take total vibration, and you can see I can put it in the in-phase component or the anti-phase component, or I can put it in quadrature component. And I like to look at quadrature. What quadrature component is are simply the elements of the vibration that produce no sound. So complete cancellation here. And you can see, again, right in this area, we have a high quadrature component. So in this area, our frequency response is going to dip, and there's going to cause other problems. Now you can see some other bumps here too. Those are important to examine. We can look at this down here, and what this reveals is a slight rocking mode. I think I have to increase. There we go. Yeah. So you can see it's rocking from there to here. And we also have a little rocking mode here too. And we can increase enhancement to that too. There we go. Of course, rocking modes are terrible. Caused by, well, they could be caused by a number of things in the motor. They could be caused by a mass imbalance. But when we have that, we run the risk of having the voice coil contact the gap and cause rubbing and buzzing and whatnot. But again, here is pretty interesting in the fact that we have a huge problem in the fact that there's a lot of cancellation going just due to phase and anti-phase happening at the same time in this. And then of course, if we move up high, we start to wind up getting some really crazy ripples.
So to generate this result, you've actually scanned however many points, hundreds of points, each point with a full frequency sweep. And so there's, and then this is all compiled into this enormous plot of the mechanical movement at every point, at every frequency.
That's right. That's right. There is some interpolation going on there. Sometimes you'll get some, there's different ways we can look at this. We can look at it in a wireframe. That is a little less taxing on the graphics card. Surface with shading, just the surface alone. That's kind of helpful. A little easier on the eyes. But again, we can, I was looking at this today and wondering, well, where is the problem here? It would seem to be in the surround. So we can look at a cross-sectional view here.
Mm-hmm.
Now, of course, we're looking at nanometers here, so this is greatly exaggerated, but
right-click and show the displacement, Ken.
I'm sorry?
Right-click and show displacement.
Oh, right. There's nanometers right there.
Right.
So, and you can click this wherever you need to click it, and it'll give you displacement there.
Right. So when you say a problem in this kind of an effect is inevitably going to occur, it's just a case of how high up the frequency range you can get. Is it fair to say?
I think, yeah, because we can't make perfect products or perfectly stiff products. Sometimes we route leads through the coil of the transducer. Sometimes there's paper thickness problems. And as well too, if you look at application use, in a PA system where we want real high intelligibility, this is a bummer right here because it's right in the middle of human speech.
Mm-hmm.
Between 1 and 2K, that could cause intelligibility problems. But in a guitar cabinet, a guitar speaker, cone breakup is good, right? So we don't necessarily worry about it too much because it's imparting those glorious harmonics and distorted tones. So, it's all application specific. So that is a really powerful component of the workbench. And I'll just slip back into the presentation there. So one of the cool things, we're talking about rocking modes is Klippel has a rocking mode analysis. So when we were talking about that 220, 230 area, where we had a full woofer rocking mode, we can use a Klippel module called RMA. And what it does is it takes the output of that information and it examines what is the cause of that rocking mode. And for me, this is quite a bit of black magic, some voodoo arts going on here that's certainly well beyond me, but examination of that transducer tells us rocking mode 1, which is dominant, tells us that there is a center of mass problem. Here we are here. And we can see how it was rocking off center, this being, at 0 degrees. And there was a stiffness, paper stiffness problem there as well. But because it's down low and in an area where you're going to get high SNR and the transducer is moving pistonically, the severity of that is considered low. I don't know if Jason wants to talk on that too much. I don't use the RMA too often, but I find it fascinating.
It looks at the laser scan data, like Kent was saying, and it isolates the individual mechanical resonances and then sees where they are. It also needs to know the small signal parameters. And depending where these resonances happen, if they're below resonance or above resonance, defines if it's mass or stiffness or BL. And it's just kind of a root cause analysis tool, like an add-on post-processing thing. Because before you could see the rocking modes and things, but you didn't know what they were. This tries to give you a cause or an effect or something, and maybe there's a tinsel lead or extra glue on it or something, or it's actually a design thing. But that's basically what this does.
Either way, I find it completely fascinating. And you can understand how, decades previous, people trying to find imbalances without this power and this level of analysis could really drive an engineer crazy.
It's fishing. I wonder, is the driver that you're showing as an example, was that lowish quality, high quality? How does that sit in the spectrum of drivers?
Bad.
I would say mid to pretty poor. There are so many trade-offs in the automotive world, just due to the fact that you need to build light. Weight and space in cars is premium. So it's really important for car audio speaker manufacturers to get the most out of their speaker with the lightest products and the least expensive products.
The reason that speakers throughout all the Klippel literature is that you get one with a Klippel system when you buy it, with a database you can run and compare it to. And it's actually pretty boring to look at a good speaker. So you want like a bad speaker to show you all the little nonlinear things and bad things they do.
I personally find it a little amusing of the acronym for RMA is kind of the same acronym that we would get if we want to return the product to the factory. Return material authorization. And I think there is a correlation, obviously. Too much.
I think so too.
Rocking modes will cause field failures and returns. They're one of the worst defects to stop before they leave the factory.
Yeah.
Yep. Especially when you well, of course, at end of line, I mean, one of the things they specifically test for is rub and buzz. Mm-hmm. And that rub and buzz is either going to be caused by a particulate in the voice coil gap or some type of crazy rocking mode that's causing the voice coil to scrape against the side. So yeah, RMA. Return authorization, please. So you can imagine how that speaker has been analyzed. So that brings us to our acoustical measurement. Now, as we know, measuring a transducer in field in free air brings up all sorts of problems. We place a microphone on axis and we try to measure that. Well, we know that sound is radiating from the front and from the back, so that's going to create what we call an acoustic shortcut. You're going to have rejection at various frequencies just because we have sound wrapping around the back. Of course, if we're not measuring in an anechoic environment, we're going to have off-axis radiation from the transducer impacting a surface and then causing problems at the microphone. If we add an anechoic chamber, of course, we can alleviate these. And if we add some type of baffle, then we can attempt to alleviate our acoustic shortcut. There's a lot of baffles out there. 60268-5 specifies a baffle that you can use. The hole on the baffle is positioned asymmetrically to reduce the baffle diffraction edge. And also it needs to be made of a particular thickness so it doesn't vibrate. I can tell you I've lived through the pain of Jason trying to make the perfect baffle and trying to not have that baffle vibrate. And it is painful, and we've come to the decision that there's absolutely nothing you can do. Everything vibrates. So you're going to get parasitic vibrations in every baffle you make. And to show you the extent that we've gone through, on the left there is what we call our high bay testing area. That is a filled and grouted concrete block baffle wall. So they're concrete blocks that are filled with sand grout. And then we have another metal baffle here, and then an insert here. And then this is a hole where we put our baffle. And this is, what is it, Jason, 9 meters?
It's 16 feet tall, that wall.
Right, 16 feet tall. So this is our infinite baffle. And we've got 0, 35, and 60. I don't know, we can put that however we want. But this was our attempt to have an infinite baffle that didn't vibrate. And there's still some parasitic vibrations in our measurement on this. And then, of course, we've got our own IEC baffle.
Something I'd like to add, though, in the that high bay room with those microphones like that, I can measure down to maybe 180 hertz, 200 hertz. Below that, the room effects make the data garbage.
Right. And we can use the room removal program within this room, but either way, both of these systems get used on a regular basis, just because we get backed up on doing transducers for not only Warkwyn or some of our clients, but also MISCO will use some of those as well. But we have just really enjoyed using the acoustic properties of the Nearfield scanner on the turntable now. So instead of the laser here, we use, we have a little microphone arm that Klippel manufactured that you get with the system. Now this is forward from the laser. So what we do is we move the turntable out a little bit to where the microphone is. And this gives us a lot of benefits, just like in the Klippel Nearfield scanner. We've got high SNR. It's very low impact of isotropic effects in the room because you're so close to it, so you don't have to worry about too much about humidity or cold and warm layers, and that gives us less phase errors. And it's powered by Klippel NFS technology. What they mean by that in this particular PowerPoint is that is the room compensation. And if you're familiar with a Klippel Nearfield scanner, that allows you to perform anechoic measurements in a non-anechoic environment on systems, speaker systems, so that we can provide anechoic data to people in 360-degree radiation balloons, frequency response, et cetera, et cetera. So they've taken that Nearfield scanner technology in mathematics and applied it here to the acoustic portion, measurement portion on this. And essentially, you don't need an anechoic room for this, and we can use a very small baffle. This explains a little bit about the holographic measurement principles. So we perform the measurement, and then there are a set of what they call Hankel functions that define the spherical wavefront emanating from the transducer. And then there's a process of removing reflectivity within the room. And in particular on the turntable, it works a little bit like this. People ask us all the time. So we've got our direct sound out, right, on axis, our direct sound out. And that is going to be impinged upon by a baffle edge diffraction problem. Here's our transducer here. At this distance is our Klippel baffle that they send with it. It's a known size. So they know where that baffle edge diffraction is. But what else do we have here? We've got an acoustic shortcut that causes problems. And we also have room reflections. All of these are alleviated because we are measuring in a 2-layer measurement grid inside of those problems. And so on the Klippel Nearfield scanner, we measure transducer systems, speaker systems, with 2 cylinders, one to capture the outgoing wavefront, and then the second cylinder to capture the reflectivity coming back to the transducer. And this double-layer grid inside these problems also works on that method. So that allows us to reduce our diffraction path and our acoustic shortcut, and also alleviates room reflections.
Mm.
And that's the round baffle setup itself. It's about 450 millimeters.
With this setup, you've got it on a table. Do you account for, say, the presence of a solid surface behind the driver, or is that treated as irrelevant?
It's treated as irrelevant. It's removed from the measurement.
It knows about it. It
Right.
knows about the stuff underneath.
Okay, so it's actually a known parameter of that measurement
Right.
setup.
Yeah, and it wants the walls 1.5 meters away.
Okay.
Yeah. Well, technically, at a minimum 1.5 meters. I mean, if you're able to measure 12-inch speakers here. So, technically you want to take into account the wavelength. I would say a minimum 8 times that wavelength to a nearest reflecting surfaces. At least that's what Klippel R&D has told me. So for very bass heavy systems, you probably want it in the center of a room. But, predominantly we're measuring 3 to 5.25 to, 8-inch systems. And we don't have that. Ours is about 2 meters away from a wall. Is that right, Jason?
Yeah, 1.5, 2 meters, something like that.
And about 6 inches deep. So we can measure a system in here, a 12-inch speaker, 6-inch deep basket.
You can also put things on top of it, like a little Bluetooth speaker, if they're short.
Right. Yeah, we'll get to the picture of it here in a second. So this is a little look at how quickly we can do these measurements. If we're doing a full-on measurement, 1,000, 1,500 points, it's going to take about 2 hours to measure that. If we assume baffle symmetry, horizontal, about an hour. But you can really just do a cross-section of it too and understand if you have any rocking modes. It's not going to tell you everything, but we can get really good frequency response in about 5 minutes.
Something about this system too to mention is, like, once you're done this measurement, you have a model of the speaker and you can generate SPL data at anywhere in space with no limit to the resolution spatially. So it's basically doing all of these measurements so it can construct a model, a point source model that mimics what it measured. And then through all of our tests and everybody's comparisons, it works.
So this brings us to our frequency response graph. And there's a couple of things to take a look at here. One of the things you want to examine here is our field separation limit. Very common. We're doing a windowed examination here, so we can window out those high frequencies. But at this dotted line is really where the holographic computation takes place. So we've got a fitted, and you can see a reflections in the dotted here. These are reflections in a room. Actually, these points, this point here and this point right here, I believe those are the actual baffle diffracted edge responses, if I'm not mistaken. Is that right, Jason?
At 450.
Yeah, 450 right there.
That's the edge of the baffle coming back to the mic constructively.
Right, there it is. So we know that, and Klippel knows that because it's a set baffle size. But they apply a fitting error here, or a fitted curve, and then remove the reflectivity, and we wind up with a radiated response there.
It's something about that speaker here in the middle of the blue part. It still has a weird table there that's not normal. That's the basket's actually flexing and resonating
right here
between 500 and 1,000. That's not supposed to happen.
Yeah, that's interesting. And so when we look at this, how do we know whether we're going to have reliable results? They also provide a fitting error in your measurement. And this dotted line is minus 20 dB, and less than anything below this gives us less than 1% error. So everything that the passband of this speaker plays is pretty good. It doesn't play very much down low, so it exceeds the feeding error there. And then up in frequency, it doesn't really do a whole lot past 10K. But in its operating range, we can say that the fitting error is good for that. And that gives us our on-axis response. This is at 10 meters. I'm not quite sure why this is so far away. Of course, this is smooth to 1/3 octave. and then referenced to 2.83 volts, 1 watt, 1 meter.
So this is
again,
actually measured with this Nearfield, but computed as an anechoic on-axis type of response.
That's absolutely right. Yep.
Anechoic half space.
Anechoic half space.
Right. And as we've had this problem showing up between 1 and 2K. That's not very good for intelligibility of that speaker. We can look at sound power as well. And it doesn't look that bad. We've got a nice descending slope, but again, we're very curious about what's going on between 1 and 2K. If we examine our directivity index, all of these graphs you're looking at, by the way, are the results of post-processing the data. Takes about half hour to post-process it, but it gives you all this. And I can look at it at 1 meter, I can look at it at 3 meter, I can look at it at 10 meter, doesn't matter. I can look at a radiation in the space of 2 pi radiation balloon. I can look at unwrapped radiation balloons, etc. In this instance, we're looking at directivity index. Big problem there. Again, that one between 1 and 2K keeps showing up. What we'd rather want is something, in a perfect world. And as I mentioned, we can look at unwrapped horizontal contour plots. So what we're looking at here is frequency response. And if the top of your head were looking right here, your nose would be looking right down the center of this axis. And this would be if we're going around the right side of the cabinet or right side of the speaker. And if we're going around the left side of the speaker, we have minus 90.
Just read out the plot points, Kent, because we can't see your cursor.
Oh, I'm sorry.
Oh, there you are.
Is that better?
Yeah.
Yeah. So yeah, your head would be right here.
Okay.
And so your nose would be looking right down this line. Over this way is around the right side of the speaker.
Yeah.
Over this way is around the left side of the speaker. Minus 90, plus 90.
Great.
If you change all the colors to numbers along the 0 degree line, that's your SPL curve.
Exactly. Yep. And you can see between 1 and 2K, that directivity goes wonky, where we have better response 90 degrees off axis. And we've got a great big hole in response there. So gets, of course, high frequency gets a little bit more directed, and then low frequency, we're just radiating omnidirectionally. One of the things that you can do that's pretty neat with the Klippel stuff now is what they call their ISC. It's the in-room compensation. So once you've performed an anechoic measurement or a measurement with the holographic parameters, it has removed that room and it knows the response of that speaker. So you can actually take that speaker and bring it into your office, a different lab. You can apply that correction curve because it knows the anechoic response of the speaker, and apply that in different measurement scenarios. And you can do that both in the 4 pi and in the 3 pi. And so it's a compensation filter that's inserted afterwards. If we look at harmonic distortion, I know Simon was interested to hear about that. Maybe grab some coffee there.
This is
here he comes. This is just
so there's always a lot of talk about frequency response. You get a flat frequency response, but that doesn't really tell you enough. That's great, but that doesn't tell you enough as to whether or not the speaker is perfect or not.
Right.
And then harmonic distortion also is not giving you enough of a picture too. So you may say we have very low harmonic distortion, but somehow speaker X sounds better than speaker Y with those things relatively the same.
Right. Yeah. We have those discussions around coffee and beer for years, right? How much can the average person actually hear? I just wanted to, as long as we're on the topic, we were just talking about the in-situ compensation module that allows you to examine that. This is just a quick examination of, these are all the distortion components in that same measurement in that room without the in-situ compensation applied. Of course, it's horrible. They're very ragged. There's not much we can glean from that. And same goes for that plot. If we apply the compensation, makes a lot more sense. So you're actually looking at THD and under an anechoic environment there. So
right.
Yeah. And then look at We see pretty high distortion there. That's probably from that rocking mode, but we also see it there. And if we look at the on-axis response, we know that that's the problem, I would say. That's the problem there as well. So after all of that, and we've defined quite a bit on that speaker, we can actually then scan in the magnetic domain. We put this, we're going to apply this Hall sensor here to the laser housing, and that'll actually insert in the gap of your voice, your voice coil gap. It might be a little bit too thick to go into tweeters, but we found it useful when we've used it in all of the reasonably sized transducers we measure. Of course, we have to tear everything apart to access that motor structure, and then we mount it right on the same turntable. You can see these holes right here. Those are the holes that we mount the turntable or the baffle above on. So you just ultimately spin the stands that hold the baffle and remove those, and you're back to having your turntable. Apply your Hall effect sensor on your laser, and then we can measure both in the phi axis and in the z axis. You can see it's raising up there. Very, very powerful measurement, and that will give us our flux density and our BL Forks factor, and this brings everything around to tell us that we have a voice coil rest position problem. We're going to move that a little bit that way. We're going to get a little bit more symmetry. Yep. My light's going out here. So that's it, really. That's a transducer summary. When you order Klippel products, you get that transducer, so you can make sure your simulations and your analyzer and your results are correct, because it's been measured so many times. We've measured it 1 million times here as well.
So it looks like there's quite a lot of depth there. Does it need a pretty high-level engineer to operate, or it just looks kind of imposing to begin with, but becomes relatively simple as you get into it?
I can operate it. I should tell you something. If I can operate it, I give the data to him down there, and he really breaks it apart.
I'd say, like with a new customer, usually we can, besides plugging things into things, we can get them like getting data within like an hour over the phone, over Zoom. It's not super difficult. If you get everything it can do all at once, it's kind of overwhelming. But if you just have a few capabilities that you learn at a time, it's not that bad at all.
Sure. And then the tricky part is interpreting results, and it kind of comes down to experience, I guess.
Yeah, but that's a much trickier part of it. That's, there's no, it just doesn't tell you, like the vibrometer and all that stuff. It told us all kinds of things that were wrong, and zero told us what to do to fix it.
Yeah.
Right. And so you can make some quick assumptions, and it'll allow you to start experimenting right away, but it's to continue peeling the onion.
So as understood it, you guys are selling the equipment, but also providing the service. So a customer could choose either way. Just please, do the analysis for me, or sell me the gear and I'll do it.
That's right.
Yeah. And what kind of a split do you get? Do people prefer just to get the service, or do they like to buy the equipment?
I would say probably the most of our time is spent working technical support issues for Klippel.
Okay.
I would say probably 25 to 30% we do contract work, but so many people use Klippel. We are quite busy between Jason and I, because we cover North America, and South America. And again, that can range from smaller companies, smaller contracting companies, and certainly every one of the tech giants uses Klippel. Mm-hmm. If you can think of a name, they use it. Sometimes they will they will send us transducers to measure with the hopes that they want to see the data the way they want to see it, with the end result that they're going to buy Klippel Klippel stuff. So they'll have a problem with their transducer. They'll ask us if we can do the measurement on the hopes that we can locate or at least give them good data. Then they see the data, then they buy Klippel.
Mm-hmm.
It's a nice vehicle.
Yeah. And when you talk about support, are we talking like video chat, screen sharing type of support, or how does it look?
Well, we will do. We primarily focus on virtual support because that's the easiest and the most economical. Certainly, we spent so much time online during COVID. We didn't do much traveling for over 2 years, so we got quite adept at doing virtual support. And of course, as the technology has forced all of us to evolve into this, what we're doing right now, that technology has evolved. And of course, every Zoom, Google, every virtual content supplier has also reinvested in Klippel because this industry has exploded. But certainly, we will travel. We have to have travel costs taken care of, but yeah, we travel and help out a lot.
Excellent.
All right. I think it's a whole other conversation on how this translates into consistency in production. So you guys can solve all the problems in the lab, but then how do we repeat that 1,000 or 100,000 times so do you find that your customers doing the design in the West and then perhaps manufacturing many places around the globe, it's kind of that translation from design into consistency over production. And I think a lot of the good factories all have Klippel already.
Yeah, I was going to say, when you do both the design and the end-of-line testing with Klippel, there's a lot of similarities and carryover for sure.
Right.
Right.
Yeah, so Klippel has what we're looking at as an R&D package.
Mm-hmm.
They have R&D and QC, and as you guys know, you can move the R&D information right into QC, and then the process of identification becomes an end-of-line decision, a marketing, a cost decision. You set your parameters through Klippel QC, and then you've got your operator at the end of the line who's just seeing a big red or a green, pass or fail.
Mm-hmm. Yeah, exactly. And actually, being locked out of China for the last 2 years, I kind of miss the sweeps walking through the speaker line. I don't get to hear them lately. So I look forward to that as things start to open up over here.
Wonderful.
So people can get a hold of you at warkwyn.com. We have
That's
your
right.
email addresses. We'll put the contact information in the description below. Simon, any more questions?
No, I think we covered it. Thanks.
I think that's good stuff. I think this is a good little dip the toe in the water type of thing to if you want to know more, reach out, talk to Kent and then Jason, and then find out if this is the right fit for your company. So thanks guys for joining us today. We appreciate it. And as always, subscribe, share, and we'll see you at the next one.
Awesome. Go THD Podcast. We enjoyed being here, and reach out to us if anybody has any questions.
Okay. Thanks, everybody.
Thanks, guys.